Hey, let's talk electromagnetism. Now, electromagnetism is obviously the combination of electricity and magnetism and how they're related. Okay, our objectives describe the factors affecting an induced potential difference due to a magnetic field lines interacting with moving charges. It takes both of those for it to happen. Number two, we're going to describe the three right-hand rules for magnetism, which tell us different things. And finally, we're going to calculate the magnetic force on a moving charge. Now, electromagnetism. Moving electric charges create magnetic fields. They just naturally do. Anytime I have an electric charge moving, whether it's positive or negative, doesn't matter, I'm going to create a magnetic field. So therefore, current moving through a wire would create a magnetic field because you'd have moving electric charges. You can verify this if you bring a compass near a current carrying wire, which I'll do in class, and you'll see that the compass needle actually turns perpendicular to a circle going around the wire. Now let's go to the first right-hand rule first. It's to find the direction of a B field due to a current carrying wire. In other words, if we have current running through a wire, what's the magnetic field around it like? You simply point your thumb in the direction of the positive I. In this case, it's going up, and then your fingers will wrap around and tell you the direction of the B field. They'll go the same way as your fingers. So essentially, grab the wire in the direction of positive current and wrap your fingers around it. So let's look at this sample. Determine the direction of the magnetic field above and below the current carrying wire. So turn your hand and where your thumb is pointing directly towards what the positive I is, and if you do that and grasp around the wire, you would realize that at the top it would be coming out of the page, and then below it it would be going into the page. Your fingers would be wrapping around like this. So out of the page on the top and into the page on the bottom. Now, electromagnets. Electromagnets are created by wrapping a current carrying wire into a coil. Coil's oftentimes called a solenoid. That's going to create an electromagnet. One unique thing about it, or one good thing about it, is if you place an iron core inside that coil, it greatly strengthens the magnet. Air core solenoids are just not simply as strong as iron core solenoids. A common place you've seen electromagnets are the door magnets that hold the doors open. They have an iron core in the center. There's a current carrying wire. The nice thing about it is if I cut off current, I cut off the electricity, so therefore those magnets no longer operate. That's why after a fire drill we have to go back and manually reopen those doors. Now the second right-hand rule will give you the direction of the B field. Now to get the direction of the B field, what we're going to do is we're going to look at the current carrying wire. It's coming in on the, we look at the direction of the current, It's coming in on the south end and wrapping around it. So what I'm going to do now is wrap my fingers in the direction of positive current flow. My thumb is now going to point at the North Pole. So that's the second right-hand rule. It's used to tell you what the north and what the south is. Now let's look at a sample. The air core of a solenoid is replaced with an iron core. The strength of the magnet will be blank to the strength before. Well, obviously the iron core makes it stronger, so therefore the answer is more than. Now let's talk about a force on a moving charge. Force on a moving charge shows the relative motion between charges and magnetic fields produce a magnetic force on the charge. Now the magnitude FB, the force of magnetic field, is equal to Q times V times B times sine of theta. Q is the amount of charge you have moving. Could be one electron, could be any number of coulombs. Velocity is the speed at which it's moving at. The faster it moves, the stronger it would be. B is the strength of the magnetic field. Generally, that stays constant. And then sine of theta is what angle you are. Now, think about that. Sine of theta, it can be anywhere from 0 degrees to 360 degrees. 0 degrees, the sine of theta would be 0, so therefore you'd have nothing. It has to have some component that's perpendicular to the magnetic field. And the direction is given to the third right-hand rule. Now the third right-hand rule simply says that B are the field lines. Now there's a lot of magnetic field lines. You have a lot of fingers, so that makes it easier. V is the direction the positive charge is moving. So therefore, I kind of think of it was hitchhiking to get you going. That's your thumb, and then the force is coming out of your palm like you're slapping somebody. So the fact that they're three-dimensional means we can't do it flat. Now that's for positive charges only. If you're going to deal with a negative charge, simply use your left hand if you're talking about a negative charge, and it will give you the direction of it. You can also figure out the direction of a positive charge and then just simply reverse it. So let's do a sample. An electron moving at 2 times 10 to the 6 meters per second perpendicular to a magnetic field of strength 2.0 Teslas. Magnetic field strength is also called flux density, so don't panic if you see that word. B is measured in a unit called Teslas, which we really haven't talked about yet. What is the magnitude of FB? So we start with our formula. FB is equal to QV B sine of theta. Pretty straightforward plug and chug after this. We know it's an electron. We know it's perpendicular. Perpendicular means the sine is 90 degrees. Sine of 90 degrees is 1, so I need to put that in there. The charge on an electron is 1.6 times 10 to the negative 19th coulombs, but remember it's a negative value. The speed is 2 times 10 to the 6 meters per second. The strength of B is 2 Tesla, and the sine of 90, of course, is 1. So you get negative 6.4 times 10 to the negative 13th. So the answer is B. I don't really need to worry about the negative because they said what is the magnitude of it. So they're not asking whether it's positive or negative. Let's look at another one. A particle with a charge of 6.4 times 10 to the negative 19th coulombs experiences a force of 2 times 10 to the negative 12 newtons as it travels through a 3 Tesla field at an angle of 30 degrees to the field. What is the particle's velocity? Well, obviously I'm going with the same formula I had before. FB is equal to QVB sine of theta, except in this case I'm going to be solving for V, so I do a little algebra first. I recommend doing your algebra before you put the numbers in. FB divided by QB sine of theta. Okay, now we plug and chug. FB is 2 times 10 to the negative 12th newtons, and then that's divided by the charge, 6.4 times 10 to the negative 19th coulombs times 3 Tesla times sine of 30. Punch it all into my calculator, and my calculator says 2.08 times 10 to the 6th meters per second. That's a reasonable number. It's going to be moving pretty high. If you ever get a number higher than the speed of light, my God, you've screwed up everything. The world will stop turning. That can't happen. Now, electromagnetic induction is incredibly, incredibly powerful. It tells you that the relative motion between a conductor and a magnetic field can induce an electric potential difference. So in other words, we can create electricity. Yay! The conductor must cut across the B field. Now, the other things that you think about is a stronger magnetic field is going to make it stronger, and faster motion will make it stronger. And then perpendicular is, of course, always the strongest because the sine of theta can only vary between 0 and 1. 1 is max, 1 is 90 degrees. Now, here's applications. The most common application of electromagnetic induction is to create electricity. And what we simply do is we take kinetic energy from something that's moving and convert it into electric energy. The wind, in this case, what we have pictured is obviously a wind turbine.
Burn the fossil fuel turbine. Wind turbine, pretty straightforward hydroelectric power. It's water that runs across the blades of the turbine, causing it to spin. Again, it can be any way, possibly. Now let's look at a sample. It shows a wire moving to the right at the speed of V through into the page. As the speed increases, will the induced voltage increase, decrease, or stay the same? Now if we think about it, we only have one magnetic force equal to, obviously F is directly related to, and F is directly related to electromagnetic force. So therefore, obviously, it's going to increase. If V goes up, they're directly related. It's also directly related to B. It's also directly related to Q. So now, in which way would you move the wire below to create a maximum voltage? And I'm going to give you two choices, that one or that one.
moving parallel to the field or moving perpendicular to the field. Well, for the one going to the side this way, obviously that's the sign is going to be 90 degrees, so that's going to be maximum. When I move it the other way, the funny thing is when I move it parallel to the field, there's actually no force created when you do that. You have to have some component perpendicular to the field. We're just touching on electromagnetic induction. We'll go into it more in AP. It's a challenging topic when you go to it to its furthest degree, but it's probably one of the most useful topics we use in physics. It's how we get our electricity, and electricity is good. Have fun. We'll go into it more in AP. It's a challenging topic when you go to it to its furthest degree, but it's probably one of the most useful topics we use in physics. It's how we get our electricity, and electricity is good. Have fun.